Welcome to this course, computational hydraulics. We are in module 4, surface water hydraulics, and in this particular lecture I will be talking about steady channel flow and specifically channel network with a reverse flow situation. This is unit number 6 of this module number 4. A learning objective of this particular lecture. At the end of this lecture, students will be able to solve steady channel flow for channel network problem with a reverse flow situation using implicit approach. Problem definition to solution. In our previous lecture, we have discussed one problem where we have considered two internal junctions, one, this is 2, and one external junction. So, this is the external junction, this was the external junction. So, now for this one we have considered 4 channel reaches, 1, 2, 3 and 4, and in this case these are the channel junctions 1, 2 and 3. For these 3 channel junctions we have seen the flow is from left to right direction. So, basically in this case we have a flow which is running from left to right direction, and this is also the direction of a sloping channel bed. That means we have sloping channel bed which is running from left to right. So, if we consider this channel bed at junction 1, so this is the up gradient or upstream location, and this part is the down gradient or downstream location. So, for channel 1 this is 1 1 and this is 1 N1 plus 1. So, we are considering that flow is from left to right, and this is our positive flow. So, according to our convention we have got all values positive because we know the flow direction, but let us consider a situation where we have a reverse flow conceptualization. If I start the same problem with flow direction in the channel 2 as flow from right to left, so this is a reverse flow situation. Now, how to solve this kind of problems, that we will discuss in this particular lecture class. So, conceptualization wise governing equations are same, but implementation wise we need to consider certain points so that we can include the plus and minus sign of these q values, because for y it is always positive, but we can have positive or negative q values during our flow problem solution, and we can have positive or negative q values depending on the conceptualization. If I consider that my flow in this small problem is from right to left, obviously I should get a minus q value at this location, because the original flow direction is from left to right. So, for this one again we will consider this finite difference discretization of the equations, and we will get nonlinear equations, and finally we will try to solve these nonlinear equations using nonlinear solution approach, that is Newton-Raphson. Now, let us see what is the problem statement for our problem. Now, let us consider this complicated network. As per this network directions, this is the lowest point, with 0 meter bed elevation. Now, starting from this 0, the values are increasing on this direction, and the value of bed with respect to this downstream endpoint is 0.15 meter. Again values are increasing, and this is the highest point in this network. So, obviously we have a slope which is towards this direction. Again from this we have, so obviously in this case your bed slope is in this direction, it is decreasing, and again for this one it is decreasing in this direction. For one, this is decreasing in this direction. So, as per the natural flow direction, these are the natural flow direction as per the slope consideration. Let us see the slope discharge condition for this one. So, this is the discharge condition on this one. Again this is higher elevation, this is lower. So, obviously flow will be from this point to this point, again the flow will be here, and this will be the flow direction for the third channel reach. So, we have 8 channel reaches 1, 2, 3, 4, 5, 6, 7 and 8. For this we have 4 internal junctions. So, this is 1, 2, 3 and 4 and red ones are external junctions or points where we need to specify the boundary condition. So, this is our point number or junction number 1. So, let us say that this is junction number 2, this is junction number 3, this is junction number 4, this is 5, 6. So, we have all total 6 junctions, and for these junctions we can see that as per the bed elevation we have the natural direction of flow. Let us say that we are considering channel reach 1. So, if we start from node 1 and move towards node 3, obviously I am considering the flow direction is according to the channel slope. So, this will be the positive direction of flow. Again, if I consider this channel 3, this is the positive direction of flow, because we are starting from higher elevation moving towards lower elevation. Again, this side it is a positive direction of flow. For channel 5 this is positive direction, channel 6 this is positive, and this is positive for 8 and 7. Now, with this configuration we can start our problem. So, we have a looped channel network, because with this internal junction everything is connected there, or every channel or internal channels, that means 4, 5, 6, these are connected. So, flow is occurring through this junction, and this junction is the main connector for the looped network. So, in this case let us consider our flow directions. So, as per our channel flow or channel bed slope, these are the directions. Now, these are the junctions 1, 2, 3, 4, 5, 6. So, if I say that my flow direction is from 1 to 3, that means I am considering that flow in this direction is positive. So, obviously for channel 1 the connecting nodes are 1 and 3. For channel 2 this is 1 and 6, channel 3 this is 3 and 4, channel 4 it is 3 and 5, channel 5 this is 5 and 4, channel 6 we have 6 and 5, channel 7 we have 4 and 2, channel 8 we have 6 and 2. So, this is the connectivity information or direction or positive direction of flow. That means, from 1 to 3 we are considering that the flow is positive. So, this is junction 1 and this is JN2 and this is L or channel reach number. Now, in this case let us consider the individual channel reaches. If I consider 1, because I have considered that the flow is from this node number 2, node number 1 to 3. So, the first node should be 1 1, that is the thing. Now, end node is 1, n1 plus 1. Like that I can discretize all in channel reaches or individual channel reaches. In this case what I am observing from this drawing, that this is 1 and 6. So, connecting nodes are 1 and 6. So, obviously the starting one is 2 1, 2 N2 plus 2. In this case it is 3 1 3 N3 plus 1, this is 4 1 4 N4 plus 1, this is 5 1 5 N5 plus 1, 6 1 6 N6 plus 1, this is 7 N7 plus 1, 8 N8 plus 1. So, these are starting and 8 1 and 8 8 N8 plus 1. So, these are the starting and ending nodes, and this is a discretization convention because we are starting with a positive flow. Now, in this case we will be considering a rectangular channel. So, obviously M1 will be 0, M2 will be 0 in this case. So, we will get simplified expression out of this. So, channel reach, this is 1, total length is 200, width is in meters. So, this is nothing but the bed width of the channel cross section. So, this is B and these are M1, M2, obviously these are having 0 values because we are considering rectangular channel. This is reach or segment length. If I consider that segment length is 50 and if I divide this 200 by 50, obviously I am getting 4 segments, 4 plus 1. So, total 5 sections. Second case also I am getting 5, third case I am getting 5 with 25 meters as segment length, fourth case also it is 5. In this case this one, this is also 5, this is also 5 and last one this is also 5. So, all total we have 1 2 3 4 5 6 7 8, total 40 sections, and all cases we have uniform bed slope and these are different n values for different channel reaches, and this is connectivity information. This is 1 3 1 6 3 4 3 5 5 4 6 5. I have changed the color for these two channel reaches, and that means channel reach number 4 and 5. I will try to show the effect of reverse flow by changing the flow direction in these two channel reaches. So, all total we will have 40 plus 40, 80 unknowns y plus q, but there will be another unknown that we will consider during discretization. Now, we need to supply junction data in this case. What is this junction data? First one, first column, this is junction number starting from 1 to 6, depth is minus 99959. So, what is this? That means there is no information available for depth, but discharge is 250. So, as per our network, this point 1 and 2, if I consider other junction nodes, these are the junction nodes. In this case, we have 1, 3, 7, 4, 5, 6, 2, 8. And externally from this node 2, this is 2, this is 1. So, as per this table, we can see that the depth is specified at downstream end at junction number 2, this is 5 meters, and we have specified discharge which is minus 250, that means water 250 meter cube per second discharge rate from this junction. And third column, this is bed elevation. Now, in this case we have all total 40 sections from all channel reaches. For 40 sections, we will get 40 into 2, that is 80 unknown values, that means y and q. Another quantity is unknown here, that is inflow or QU at the starting node 1, because in this case only y at downstream and QD, if I put negative sign because I am extracting water from the system from this particular point. So, this is minus QD. So, these two values are specified. So, this QU is essentially unknown. Now, if I add this QU as unknown, so all total we will have 81 unknowns in this case. Now, for this channel 3 or node number 3, 4, 5 and 6. So, for channel 1, channel 2, 3, 4, 5 and 6, we will have all total 4 is the number of segments per channel reach, 4 into 2 is for one continuity, one momentum into 8. So, this is the total number of equations that we will get from the individual segments. So, 4 into 2 into 8. So, total number is 64. Now, for this internal junctions 3, 4, 5, 6, that means we have 4 junctions or internal junctions. For 4 junctions we will get 3 conditions, that is 1 continuity, 2 energy conservation conditions, and this will get 12 conditions out of this. Now, after that, if we consider this external junction node 2, we have one depth and one discharge condition, plus there will be energy continuity condition. So, all total we will get 2 conditions for one for specified depth, that means 2 for depth, 1 for discharge continuity. So, we are getting here 3 equations. Now, at this node number 1, so if I add now 64 plus 12 from our, this is coming from segments, these are coming from internal junctions, plus 3 here which is coming from external junction node, plus 2, 1 for discharge continuity at node number 1, plus 1 energy continuity for this channel reach 1 and 2. So, all total 2. So, if we add this, so we will get 17 plus 64, which is 81. So, we have 81 equations and 81 unknowns, but what we can do, we can directly specify this QU value during our calculations. So, obviously, we can directly specify this 250 meter cube per second value here, and we can reduce one variable, one unknown variable, because inflow from this particular node, which is node number 1 or junction node, external junction node 1, should be equal to QD, which is coming out from this junction or external junction node 2. Now, if we see this last column, these are bed elevation for different junctions. Now, what is required? We need to estimate the flow depth and discharge across the channels. Problem definition, that was a problem statement. Now, we have governing equation for channel flow. This is continuity equation, this is momentum equation. Now, in discretized form, for different channel reaches and different segments, we can consider different sections, and for different channel reaches, if the flow is from section 1 to NL plus 1, we will consider that flow is positive, and if this QL is negative, we will consider that this NL plus 1 to 1 is the flow direction. Now, if we consider this as positive flow direction, obviously we are extracting water from junction node J and we are adding water to this junction node J plus 1. So, this is the sign convention for this one. Now, in discretized form, for ith channel segment of the lth channel reach, we can write this continuity. This is CLI, this is valid for lth channel reach and ith segment. Now, we can get the coefficients of our Jacobian matrix from this one. Now, if we discretize our momentum equation, this is somewhat different compared to our discretization that we have discussed in our previous lecture class. In our previous lecture class, we have considered this as q square by a square, q square by l square. This is also q square because in that case all values were positive, but in the present case we will consider this quantity, which is the quantity for SF or friction slope, will change this q square with q and mod of q. In that case we can get the direction of your of friction slope. Now, obviously in this case we have NL nonlinear equations with NL plus 1 into 2 unknowns, discharge and flow depth. If we write the elements of our momentum equation, this is important because in our previous lecture class we have considered all q square values in the coefficients of this Jacobian matrix also, or entries in the Jacobian matrix, but in this case the terms which are related to q square by a square will not change or will not change that to q abs q, only the terms which are related to friction slope will change the sign. In this case this two terms are related. In the next case for the derivative calculation of MLI with respect to QLI, we will consider this mod value here, but for first term we are not changing any or we are not taking any absolute operator here. In YL I plus 1 also first term we are not changing that, but for second term we are changing it. So, in this case we will get another QLI I plus 1. So, obviously this term will change to mod value of q. Now, so compared to our previous one, what are the changes in this derivative calculation? So, change terms are 1, 2, 3, 4, 5 and 6. These 6 terms which are related to friction slope will change those terms. For trapezoidal channel section this is dA by dy, but we are considering M1 M2 is 0. So, obviously this will be B dr by dy. So, obviously we will get a simplified equation for rectangular case. Now, this is the algebraic form. We have talked about our continuity momentum equation discretization, but we have not talked about the discretization of individual internal junctions and our external junction boundary conditions. So, we have all total 6 junctions. In this case, the outer one starting from 1, this is 2, we have 3, 4, 5 and 6. So, obviously, this is our condition in this case. So, one by one let us consider the conditions for different junctions. So, this is junction number 3, 4, 5 and 6. These are our channel reach numbers 1, 2, 3, 4, 5, 6, 8 and this is 7. So, for channel reach number 1. So, for channel reach number 1, what condition for discharge we are getting? For discharge or continuity, we are getting that this QU, this amount we are adding, and Q1, this is being extracted from the system. So, Q1 1, this is negative, minus Q 2 1, this should be equal to 0. So, QU amount is added into the system and this amount is being extracted from the system as we have considered our flow directions from 1 to 3 and 1 to 6. Next condition, because we are not considering the difference in elevation for this junction and our channel reaches. So, for Y we will have one condition. What is that? That is Y 1 1, this should be equal to Y 2 1. That means, first section depth at channel 1 and channel 2 should be same, provided that we have same elevation for these two channel sections. If we consider the flow or the conditions for section or junction node 2, we will have Q or Q7, this is N7 plus 1, this is added, again Q8 N8 plus 1, this amount is added to the junction, this is for junction number 2, and extraction is QD amount. So, this is the continuity condition. Again we will have another condition that is Y7 N7 plus 1, this is equals to YD, and Y7 N7 plus 1 equals to Y8 N8 plus 1. That means, we have two conditions for Y and one condition for discharge at the downstream external junction boundary. Next is for junction number or junction node number 3. For 3 we have discharge from 1. From 1 this is N1 plus 1 which is being added there, minus Q 3 1 this is being extracted, then Q 4 1 this is also extracted from this node. So, this continuity condition should be satisfied, and we will have y 1 n 1 plus 1 equals to y 1 y 3 1 and y 1 n 1 plus 1 this is equals to y 4 1. So, we will have two depth related condition or energy conditions, one our continuity condition. Obviously, in this case I am considering the our junction loss thing. During in junction we do not have any loss condition. If I consider the channels 4, so obviously for 4 or junction node 4 we have 3, that means Q 3 N 3 plus 1 this is being added. Also the amount which is added is Q 5 N 3 or N 5 plus 1 minus Q 7 1. So, this amount is extracted. So, obviously, in this case we will have Q 3 N 3 plus 1 or this is for depth condition. So, obviously, this will be y equals to y 5 N 5 plus 1 and y 3 N 3 plus 1 equals to y 7 1. So, two conditions here and one for discharge. Similarly, for junction node 5, this amount is added Q 4 N 4 plus 1, also Q 6 N 6 plus 1 minus Q 5 1 this is equal to 0. So, y 4 N 4 plus 1 this should be equal to y 6 N 6 plus 1 and y 4 N 4 plus 1 equals to y 5 1. So, 2 1 again 3 and the last junction, that is 6. For 6 this is connected to our this is 6, this is connected to 1, 6 and 8. So, in that case this is 2, 6 and 8. In this case we will get Q 2 N 2 plus 1 minus Q 6 1 minus Q8 1 equals to 0, and this will be Q2 Y2 N2 plus 1 equals to Y6 1. This is Y2 N2 plus 1 equals to Y8 1. So, these are the conditions. Obviously, if you want to get the elements of Jacobian matrix for this one, we can differentiate with respect to the variables. In this case, so obviously on all these values are unknown. So, we have 1, 2, 3, 4, 5, 6, this is 1, 2, 3, 4, 5 and 6, total 6 unknowns are there in these 3 equations. So, we can write the elements of the Jacobian matrix from this calculation. Now, after getting this elements of the Jacobian matrix, now we can construct the total Jacobian matrix and we can get the solution out of that. But for implementation purpose, we need to input certain information in certain format. First is channel CHL inf, which is channel information. First column is channel reach number, second column is total length of the channel, third one is width of the channel, fourth and fifth one, these are M1 and M2 values. This sixth one, this is segment length, this is N, this is S naught, and the last two, these are junction node number 1 and junction node number 2 for any channel reach. That means, channel is connected from 1 to 3, 1 to 6. Next information we require is that junction information, and in junction information we can include the boundary condition, and in the last column we are providing this elevation values for different junctions. Now, junction connectivity, this is another important parameter. For junction 1, this is starting from junction 1, 2, 3, 4, 5, 6. For 6 junctions, we have this condition. So, for junction 1, we have 2 channel reaches connected to it, that is channel reach 1 and 2. So, this is the starting sections for channel reach 1 and 2. So, we have plus 1 and plus 2. For channel reach junction node 2, we have 2 connected channel reaches. In this case, -7 and -8 means end sections are connected to this channel reach 2. Channel junction 3, in this one, the end section of 1, starting section of 3 and 4 are connected. Channel 4, we have end section of 3, end section of 5 and starting section of 7, that is connected. Channel junction 5, we have again 3 connected channel reaches. -4 means this is the ending section or end section of channel reach 4, end section of channel reach 6 and starting section of channel reach 5, these are connected. And channel reach or junction node 6, we have 3 connected channel reaches. This is the end section of 2, starting section of 6 and starting section of 8. So, these 3 matrices, these are required as input in our program. With this information we can calculate the values